The talk that I'm going to present is a bit different from quantum computing, but then what I'm going to present is the materials per se, which people are going to use in the next perhaps 20 years and come towards quantum computing using such kind of materials. So I'm a materials chemist and I mainly work with nanomaterials. So, and in particular from the nanomaterials I've chosen the field of semiconductor nanocrystals, which are more popularly known as quantum dots, as it has been popularized by the biologists. What I'm going to discuss today is the main aim would be to give you a brief introduction of these quantum dots or semiconductor nanocrystals. The most important aspects are the electronic structure of these nanocrystals, the optical properties, and I'll discuss a few of the applications. So I've just entered into the world of applications and devices. Okay. So we are basically a materials group and we make semiconductor nanocrystals. Now this is a very representative picture of fluorescent cadmium selenide quantum dots. So these are all cadmium selenide quantum dots, but different sized particles. I'll come to this in a moment as to why these things happen, why these spooky events happen, that some cadmium selenides are green and the others are red. We made these things and a few more, and we do a lot of fundamental studies on these particles. That is our main aim. So these kind of fundamental studies, some of them are basically related to the electronic structure and luminescence properties. I didn't have a much better visual for that. But that just depicts that different atoms on the nanocrystal behave differently and contribute a lot to the property of these, particularly the luminescence properties of these particles. We do single particle measurements on these quantum dots. So because what the idea is finally to use these materials on a single particle level. And these materials are typically between 2 to 7 nanometers, cadmium selenide quantum. We collaborate a lot with biologists. They kill these innocent rats over there by injecting loads and loads of cadmium selenide nanoparticles and magnetic nanoparticles. The most commonly ones, or rather the most only approved ones, are iron oxide, Fe3 or 4 nanoparticles, and do a lot of fluorescence and MRI studies with them. The devices that I've got into recently are basically light emitting devices. Since these particles have efficiencies as high as about 90%, you've got to use them for something. This particular CIE, the chromaticity curve, shows you a blend of these nanoparticles with some polymers, and you can actually traverse the entire white regime. So for daylight, for room lighting, for example, you prefer warm white light, which would lie in the yellow region, close to the yellow region, so it has a slight yellow tint. And for other purposes, for some shops and all, you prefer a blue tinge, you want a cool white light. So those kind of things is what we've done. There are some sensors. So in particular, these are alcohol sensors. I'll just give a brief description of this particular thing also, using the fluorescent properties of quantum dots. And recently I've started working with photovoltaics, thanks to Dr. Mehta, who's been helping me a lot with this. Okay. So a brief outline of my talk would be a small introduction to what semiconductor nanocrystals are, something about electronic structure calculations and why they can be very, very important, the structure of nanocrystals and how this structure is related to luminescence properties, since these are the most important ones in case of quantum dots, and 3 of these applications which I'm going to talk about. Okay. Now people talk of nanomaterials and people talk of 100 nanometers, some people talk of 200 nanometers. I mean, the officially agreed value is between 1 to 100 nanometers. For me, it's still a narrower range. between 2 to 20 nanometers. It doesn't matter what the size is actually. What matters to me, my definition for nanomaterials is that the property must change as a function of size. And if that happens, I'm ready to agree even a 1 meter long thing to be called as nanometer or a nanoparticle. It doesn't matter. Okay, but that's the only difference between bulk materials, molecules, and something intermediate in between. That something has to change as a function of size. Of course, they have a huge surface to volume ratio. And because they have a huge surface to volume ratio, typically a 1 nanometer particle has complete surface, nothing. There's nothing like a bulk. So, a lot of properties, and in particular luminescence, is governed by the surface atoms. We'll have one of these examples in today's presentation. Most of the properties are governed by confinement of charge carriers in semiconductor nanocrystals. For the benefit of students, I'll mention this briefly. And in the literature, you'll find different words being used interchangeably, nanoparticles. When they are crystalline, you would prefer calling them nanocrystals or quantum dots, because they have some confinement, and you see this quantum confinement effect. Nanoclusters don't fall in the regime of what we are talking. They are more rigid structures, and we leave them out for the moment. Okay, this is just a slide to show you that most of the semiconductors that we are working with are tetrahedrally bonded. This is the way we build these nanocrystals when we want to calculate any electronic structural property of this. Now, for the benefit of those, this semiconductor, a bulk semiconductor material, is characterized by the valence, the fill band, and the conduction or the empty band. And there's a well-defined band gap. No matter what, how small you make this semiconductor in the micrometer regime, you take this small crystal or this large crystal, the band gap is very characteristic. But and for a molecule, on the other hand, you have the highest occupied molecular level and you have the lowest unoccupied molecular level, and that's very characteristic. For a molecule, you can't change that. But when you come to nanomaterials, when you start changing the size of these bulk materials and shrink it down, you come to a regime which is known as the quantum confined regime. Well, in very simple words, what I can remind the students is that this is akin to a particle in a box-like situation, where you have, for a one-dimensional box, for example, you have n square h square by 8 ml squared, and you change the length of the box, so you decrease the length of the box, increase the energy level separation. That's exactly the same thing that you're seeing in these particular quantum dots. So you're going to decrease the size of the nanocrystal, you increase the energy level separation, or that energy level separation can be correlated with the band gap, and as you increase the band gap, you're going to increase the energy required to make this transition across the band gap, and you can imagine if it's a smaller size, more energy is required. That means this color of these nanoparticles, which is nothing but the transition from the conduction band to the valence band, is going to be in the blue end of the spectrum, and if you have large particles, then you're going to get red colored fluorescence. Okay. Some importance and uses of semiconductor nanocrystals, most of them I've just discussed, but one thing is tunable electronic and optical properties. So you have the same material, you don't need to change the material, you can tune the properties. The good thing is that they have a very broad absorption spectrum. I'll show you some of these spectra. And a very narrow emission spectrum. That means I can excite these particles at any given energy. Energy, of course, above the band gap, not below the band gap. So I can excite it at any energy, but I'll get only one single very sharp emission. So that means if I have a collection of particles lying over there, I can excite all these particles with one single source, somewhere in the ultraviolet, let's say. And then they're going to all emit. So that gives me a possibility of something called multiplexing, or studying different colors at the same time. They are very good. These particles, I mean, when people started research on semiconductor nanocrystals, these were not even stable for hours. But today we can make things that are stable for more than 3 years. They lie in the solution and still shine. The good thing is, compared to dyes which have been used for some applications, not all, but some of these applications which dyes have been used, dyes degrade within 5 minutes of laser irradiation. So you have to reduce the power, so that means you have to get more noise in your data. But nanocrystals don't degrade for weeks. You can continuously shine lasers in them. We'll not go into those reasons. Biological tagging applications will not, so that's why they are better than the present fluorescent tags. Some of the applications of light emitting devices we'll discuss. Light converters, solar cells. Now, since she's asking for royalty, I'd better not go into that. We do deal with some of the infrared emitting materials such as lead sulfides and selenites, but we are not into waveguides or telecommunications, but some of the people do work on those aspects too. Okay, so for the synthesis of these nanomaterials, there's some of the methods you will find in literature, like in fact Dr. Mehta described one of the methods for metal nanoparticles, which in fact I had not heard of earlier, but seems very impressive and makes very nice and monodispersed particles. Now, the main aim is to make high fluorescence particles, and since we're going to make some studies, for applications I don't think people are going to bother too much if there's a huge distribution. So what you want is a narrow emission spectral feature, and what you want is a very narrow size distribution. So, some of the methods like microwave synthesis or solvothermal synthesis, for example, these give you a rather broad size distribution. But this particular scheme where you can separate nucleation and growth, that means you have the atoms and you first form a nuclei on which more and more atoms get deposited to form the particles. So you, at one point you are making the nuclei and then just growing them over a certain period of time. What would happen if you make some nuclei at this time, then we would get some particle size distributions. So these kind of high temperature methods ensure that you separate the nucleation and the growth. So you can get more monodispersed particles. I'll show you some of the transmission electron micrographs, and you can see that these are actually less than 5% size monodispersed. Some of the particles sometimes you need to make in water, for example, in particular for biological applications. Water is the medium. You can't make many of the particles to luminous in water. The reason is that you don't have so many precursors to start with to make these particles. Maybe we keep trying new and new things. Maybe someday we'll have more. Presently, only cadmium telluride is the one that has been successful. Okay. So, as I was telling you, that as you change the particle size, you change the band gap. So you have a very small particle over here, and it absorbs at about 520 nanometers and emits at about 530. There's a small Stokes shift. So, and as you keep on heating it for longer and longer times, you see this peak is shifting towards the red end of the spectrum. That is the size of the particles is growing. Okay. Okay. This particular slide just collects all the spectra and shows you that you can tune the size between, so these are different synthesis methods, not from one synthesis, but you can tune the size so that you can get emission from about near ultraviolet to near infrared. And this is the emission. So I was talking of broad absorption spectrum. You can see that if this fellow starts to absorb over here, it keeps absorbing all throughout. But the emission is just very narrow. Typically the full width at half maximum is 25 to 30 nanometers. And I was telling you about the size distribution. So these particles are, now I forget the values, but I think these are about 2.5 nanometers roughly in diameter. And these are about 2.8 and that's about 4.2. But don't quote me for the numbers. But you can see that these are very monodispersed in size. And all of them are very, very crystalline. we do an X-ray diffraction experiment. There's something called the Scherer equation, from where you can get the size of the nanoparticles or the nanocrystals, to be exact. I should be more careful using this word, nanocrystals, because the X-ray diffraction size that you get is only for the crystalline part. And well, if Professor Mehta is, angry with me one of these days, I just don't go to the PM, I go to the X-ray diffraction and immediately get the size of the particles. But normally he's not, he's in a good mood. The other thing is also you can try to align these particles and form superstructures, and if you form superstructures, then the X-rays will diffract between these particles, and you can get these low angle peaks, which according to the Bragg equation would correspond to the ordering of these particles. Publicity, we can make different shapes, we can make very monodispersed spheres, we can make wires, we can make nanorods, we can make tripods, and all of them have various applications. For example, think of tripods or tetrapods, and if you want to make use of these kind of materials in LEDs or photovoltaics, you always want a contact, and you want a contact in a particular direction. So if you want the central sphere to be sitting on the bottom electrode and the rod to be pointing out, then tetrapod is the only way you can ensure it, because it's going to always sit on its three legs. Okay. Okay, so much so for the introduction to the world of semiconductor nanocrystals. I'll move on to electronic structure calculations. And so I just mentioned briefly that you can use, for example, the particle in a box model. So the particle in a box model for a spherical particle with infinite walls, and also if you agree to use an effective mass instead of the free electron mass, is known as the effective mass approximation, and was proposed as early as 1982 by Louis Bruce, so who's considered to be one of the fathers of nanoscience. But then, the problem with that particular, it's quite qualitative, it agrees well, and everybody understands why some things happen. But why exactly those things happen to that amount is not given by an infinite potential in a infinite potential well model. What you need to do is either decrease the potential, which means you're going to play around with the parameters and try to bring it to match your experiments, or go on to more realistic models. So more realistic models are of course based on chemistry, not on physics. Physics is like that spherical tau approximation. Yeah. Kids, you've heard of that? No? A tau is a sphere, The tail is useless, chop it off. The legs are so small, get rid of it. What's the head doing? Get rid of the head. So it's a sphere. So you can approximate a cow to be a sphere. So that's how you get the results from physicists. So what we do is something called the linear combination of atomic orbitals. So if you've already studied this, it's like making the hydrogen molecule. You take two of these energy levels and make the bonding and anti-bonding. Now, you do it for 1,000 atoms. Yeah. So that's, in fact, physicists have also somehow stolen this idea from us, and they call it the tight binding method. So what they do is to get the on-site energies, which means the energy levels of these orbitals, and the hopping parameters, which means how much they interact with the next orbital, with the next neighbor or the second next neighbor, all these hopping parameters. So if you account for all of them, you can get all your dispersion curves, and you can get the band structure of these particular materials. So this thing is called the linearized Muffin-Tail orbital method, but we'll not go into those details. What I wanted to show you was, we are interested in the band gap. And something we get from the LMTO matches pretty well with the tight binding methods. For a 76.5 angstrom, those days I was using angstrom instead of nanometers. Nanometers is more fashionable now. For 7.6, roughly 8 nanometers nanocrystal of these semiconducting elements, it's no longer a nanomaterial, it should resemble more of a bulk. Yeah? You can see the black lines exactly match with the red or the blue ones. So you're getting the exact band gap, so you can actually go down to smaller sizes, and once you go down to smaller sizes, you can get the electronic structure or the electronic properties of these materials. So let's go down to some small, oh great. Everything summarized in one sheet. 2,6 semiconductors, the chalcogenides of zinc, cadmium, mercury. Mercury is not here, okay. So this was in 2004. Excuse me. Till then zinc telluride was not so much studied, but you can see that the black line, the solid line, represents the results of the tight binding calculations. The effective mass approximation, or the particle in a box method, is represented by that dotted line. And somebody else prior to us had managed some different kind of a model. So that comes pretty close to what we have done, but not exactly as close in all the cases. So that's how you describe the variation of band gap with size for semiconductor nanocrystals, various semiconductor nanocrystals, 2 6s, 3 5s. So very important ones are all here. Yeah, all the people doing lithography are more interested in these kind of 3 5 semiconductors. Okay, now that Manish is here, maybe I can go on to one of these, which is called, he's already mentioned it, manganese doped gallium arsenide. It's a half metallic ferromagnet. And the question that physicists kept asking is, see, the device structure are typically 50, 40 nanometers these days, and they keep asking, oh, what's the use of going down to sizes? Will we have the same properties at very low sizes? Can you calculate that for us? And he said, okay, it's a tough job because you have to calculate 2 different spin channels, and you have to worry about doping manganese into this, so your supercell gets larger and larger if you have less number of manganese. So what we did was we finally managed it, and the results are plotted here. The thing is that it's because of the d orbitals that are present. Sorry. It's the d orbitals that are present in the highest occupied levels, so that's in the valence bands. They contribute to the half metallic character. And what happens as you keep coming down in size? Do we retain the half metallic character or not? The answer is that we do, up to about 20, so coming from the bulk, up to about 20 nanometers, 20 angstroms, or 2 nanometers, we do retain these properties, but then it seems to drift. I'll just schematically explain that. So that's like the 5b electrons of manganese over there, manganese 2 plus goes into gallium 3 plus, arsenide 3 minus. So it's a whole dope system. We have just 4 electrons, 1 for the whole. Okay. So since this is lying deep in the valence band, it can't be whole dope. So the top, because the whole has to float to the top, so the whole comes on the top. And as you keep on changing the size of these particles, so that means you're essentially increasing the band gap. You're increasing the band gap, but you cannot do anything with the manganese D levels. They are already atomic in nature, so they will not shift. There's no confinement effect on those things. They are already, so as to say, confined. So they stay at the same position, and at some point of time, the whole tends to lie on manganese D levels. So that should correspond to somewhere over there. And if you keep on further decreasing the size of these particles or increasing the band gap, the manganese level is going to come on top. Right? And then this hole is no longer going to lie on the valence band. It would like to float up. Right? And what would happen is some kind of a valence transition from manganese 2 plus to manganese 3 plus. So as good as about 2 nanometers, you don't have to worry, go down in size. Okay. So that's about some of the calculations, but I'm more of an experimentalist and that's closer to my heart. So let's come to the structure of these nanocrystals and how we can explain the luminescence properties based on the structure of nanocrystals. There are two methods which I'm going to discuss. One is luminescence itself, and the other one which we've used is X-ray photoemission spectroscopy. So basically exciting electrons or pulling them out of the solid and analyzing the core levels and the valence bands. So mostly the core levels in this case. So shown on the left is something called a universal depth curve. So if the electron is coming out with a lot of energy, then it can come out from deep under the solid. If it has less energy, then it cannot come out from deep under the solid. Yeah. If it has more energy, it can kick everybody around and just come out. Right? That's the concept. And that's the concept you're going to use. And shown over here is a representative. So what we did was to make 3 different samples of zinc selenide core and cadmium selenide shell and keep on increasing the shell thickness. And you can see over here that if the shell is very thin, you can observe some zinc signal. So it's all normalized to the cadmium peak, don't worry. If the shell is thicker, then you have much less zinc and hardly any zinc. So when the shell becomes thicker and thicker. So you can actually analyze where exactly the electron is coming from and what its oxidation state is going to be, and based on that you can tell a lot about the luminescence properties. For example, in lead selenide nanocrystals, which was the most interesting case till now. So you do all these experiments. What you have to do is get access to different energies, different X-rays. So you have to go to a synchrotron center. So we did all this in Electron in Trieste, Italy, and you get all these data. So we will not discuss much about what this data means. Okay, maybe one of these. So if you see that the black ones is what our data is in the solid lines, the red and greens are the fits. So I can decouple my data for 2 different species of lead, and 2 different species of phosphate. And finally, I'm going to assemble all this data into the form of a model. I'll not discuss the details, the gory details of this. Okay. So the model comes out to be that you have a core over here, which is very good crystalline lead selenide, and then you have a non-stoichiometric shell of selenium present on top of it. And from the analysis that we do is that as the particle grows, okay, this non-stoichiometric shell keeps on growing. Okay. And subsequently, the fluorescence intensities keep coming down as a function of size. Okay. The other important thing, or very interesting thing, is something called core shell structures. There are 2 different kinds of core shell structures. One is called a type 1. So these are representative of the band gaps. So let's say this is the valence band and this is the conduction band of the core material, and that is for the shell material. Now if you have this kind of a core shell structure, where you have the band gap of the shell much higher than that of the core, you're confining both the electron and hole inside in the core. Right? So once you excite it with light, you're creating this electron and hole and confining it inside. So that means they have a greater chance of recombination. So you'll get much better luminescence efficiency. So these kind of type 1 structures are much better for use in light emitting devices. Whereas the type 2 kind of structures, where you have such kind of band offsets, the hole would like to float to the top over here, and the electron would stay over there. So you have separated the charges, and those kind of structures are more feasible for photovoltaic applications. So this one I'm going to discuss about light emitting materials. So this is cadmium selenide core coated with a zinc sulfide shell. A very interesting thing. was that it really depends on the kind of surface atoms that you have. Surface plays such an important role. So if I coat one monolayer of zinc, okay, the fluorescence intensity shoots up. But then if I coat a second monolayer of sulfur on top, intensity comes down. So zinc is very crucial. Although the coating is because of zinc sulfide, the type 1 structure that we are forming is because of zinc sulfide. But sulfur on the surface brings it down. Why is that? Because the ligands that are attached on sulfur are really horrible. So you really need, and this people don't know till now, I mean, you really need a cation-rich surface to get a very good luminescence efficiency. That's just, okay, what we thought was, let's coat it partially. We don't coat a full monolayer of zinc, but let's coat a partial monolayer of zinc and see what happens. So what happened was typically about 50% of zinc coverage, and you get the maximum fluorescence intensity, and then it flattens out, and when you're coating sulfur, it falls down. So why does it flatten out over here? What we had in mind was, is all the zinc going onto the particles or not? And when we did some of the atomic absorption spectra studies, we realized that when we are putting 25%, only 5% is going, 8% is going on the surface. And when you're putting 50%, only 17%. Now, what's so special about 17% and 8%? And what we realized was, there's a great deal more to these nanocrystals. They all are crystalline in nature, and each crystal has facets or faces. So different faces. And different faces have different energies. And when we compared these different facets, what we realized was that some of the most reactive facets belong in this 8% of zinc coverage. So first, zinc comes in and attacks all these very reactive facets. Gain of intensity. Then 17% corresponds to the next reactive set of facets. So the surface of these particles is really so important that it plays an immense role in the luminescence properties. Moreover, we could even see that the type 1 structure for a cadmium selenide would be formed only when you have a larger band gap material. And the only two larger band gap materials that are known in case of sulfides are cadmium and zinc sulfides. So this immediately acts as a very good sensor for cadmium and zinc, giving a high intensity in the presence of cadmium and zinc, whereas it does not sense any other ion. Okay, so since we've come to sensors, how much time do we have? I have some time. So since I've come to sensors, let's go on to some of these applications. First, the ethanol sensor. Now, the thought was about breathalyzers, but I don't really think we've been able to market these things. This is a poly-2-vinyl pyrrolidone. Now, these kind of polymers shrink or swell depending on the environment. And the good thing about this particular polymer is that in ethanol, it swells up, it opens up. And in toluene, or even in dry state, it remains shrunk. So we attached these beautiful quantum dots on top of the polymer. And when it's in a shrunk state, when it's all collapsed like that and all the nanoparticles are trapped inside, so we are shining this laser from here, a green laser, and we don't observe much light. But when it's in a swollen state, the particles come out and we do observe a lot of intensity. So that's the kind of thing I'm talking of. In ethanol, you see a very bright, intense thing. In toluene and in the dry state, it's dark. So, and the good thing is very, very linear, so you can know exactly what content of ethanol is present over there in the environment. Okay, moving on to light emitting devices. What we realized was that, and it's from the Sandia National Labs, they have a lot of work going on for white light emitting devices, solid state white light emitting devices. About 20% of electricity world over is used for lighting, nothing else. Okay. So we do need solid state lighting, and it can compensate by about 50%. And since our nanocrystals have efficiencies as high as 90%, why not use these? So what we did was to try 4 different methods over here. I'll discuss a bit of each. First thing is to mix all of them. The second thing is surface state emission. Now I've already told you the importance of surface. So surface state emission is something in the core shell structures, or rather core shell structures. These were, I think they were in 2005 when they first came in. These are more like atomic layer deposition techniques to make multiple thickness films. So, and dope nanocrystals. So let's go on to blends. I mean, you just need to do is synthesize the blue, green, red particles, mix them, and try to mix and match and get the shade of white light that you want. So that's engineering, not chemistry. Surface state emission. Now the thing is that you have a lot of surface states on nanoparticles, and all these surface states are typically, you can think of them that, for example, a tetrahedral bond. An atom inside in the bulk has all 4 bonds or 4 valencies satisfied, but an atom on the surface would have either 1, 2, or 3 bonds pointing outwards. So those are called dangling bonds, and dangling bonds means they are electronically, they are placed at more or less the same level where they started with as atomic orbitals. Right? So they are not shifted anywhere because they have not bonded to anything. And if they are not shifted anywhere, they would lie between the HOMO-LUMO or the conduction band, valence band, so within the band gap region. So these green ones are what I'm showing you as the dangling bonds. Now, interestingly, if these dangling bonds have transition dipole moments so aligned, which of course we have no control over as of now, but if they have so aligned that there is a definite possibility, so the possibility of transition is non-zero, then we can get emission across these. And that emission would be less in energy compared to the band gap energy. So what I have to do is cleverly make a particle with lots of surface states, right, and choose the emission of the band edge to be somewhere on the edge of ultraviolet blue. So when you have a sharp ultraviolet blue peak, and when these states come in, they will automatically be lesser in energy, so they'll take care of the green, yellow, and red regions. And if I can tune that emission, I could get very good white light emitting particles over here. And by doing some good chemistry over there, you can actually tune the surface. But you cannot tune the intensities so easily. They just happen to come. Okay. We've made one of those light emitting devices with that. I think I have a picture later. Now that's another interesting concept, where you have emission from the core and another emission from the shell. So you've managed to insulate the core and the shell material and have 2 different emissions. So the emission from the core is somewhere in the yellow-orange, 600 nanometers. And what I want is the emission from the shell be somewhere in the blue cyan. So if blue cyan plus yellow-orange mix up together, then what we are going to get is white light emission. So that's interesting. So I keep on making a shell around it, and I start getting some emission from the shell, and I do some tricks over there, which are basically heating and beating of these nanoparticles, nothing more. And you can actually play around with the intensities. And over there, what you saw is a traverse through the CIE coordinates, touching the exact center of the white point, which is 0.33, 0.33. But actually white is more well defined as a region rather than a single point. Good. People asked us, are you sure they are core shell structures? Sorry, from that far you are not sure. But you can calculate the size from the core shell structures, get all the numbers, and what you get from your calculation is 6 nanometers and 5.8 nanometers from what you get from this TEM image. There's energy transfer from the shell to the core materials that clearly shows that these two are definitely connected together and they are not floating apart. They are not two. The main question that comes is, are these two separate particles or are these connected together? Okay. Now, since I talked about gallium manganese arsenide, the other dope system which we have been looking at is zinc manganese sulfide. I will not go into much details over here, but zinc sulfide surface state, defect state or surface. Well, most of the defects in a particle are on the surface, since most of it is the surface and all of them are dangling bonds. So, defect state emissions and manganese DD emissions. Manganese DD emission is typically around in the yellow region. You get some blue defect state emissions. Combine them, get some white light emitting particles. The only drawback till now with zinc manganese sulfide is that they are about 1% or 0.1% efficient. We need to increase the efficiencies. But these are going to be really good for the future because cadmium is something people are not going to accept very easily. Okay, one of the devices, one of the light emitting devices we made was something like that. Indium gallium nitride, UV light emitting diode, and on top of that we put our cadmium sulfide. So it basically fosters energy transfers, which is giving an excitation to the cadmium sulfide, which has a lot of surface states, and it's going to emit white light. So that's a real working device over there. And this was the one that I showed you in the very beginning as a glimpse to. Okay. So, in summary, what I've told you is what nanocrystals are and their possible applications, some methods to determine the electronic structure and the internal structure of nanocrystals and the surface of nanocrystals, and some of the applications in sensing light emitting devices. And did I miss out photovoltaics? Yeah, I've just started that. And this is a new concept that we are trying to use. Since you're getting an electron separated from a hole in this quantum dot, nobody's used this kind of method. I mean, they've all blended with polymers and let it go. Okay, let's see. What we're going to do is give some bias to it. You have an active material over here and put some hole transport and an electron transport layer. So once excited, the electron would actually prefer going to a lower lying level and the hole would prefer rising. So this is the kind of stuff. We are actually designing organic molecules. We've just started this work and Dr. Mehta is helping us with all the measurements possible. Okay. That's my group currently. And who actually do all the work. I sit over there. Acknowledgements to my previous groups, because some of the work, a part of that work which I showed you, or rather a major part of that work which I showed you is from my postdoc and PhD, a bit of it from my PhD. Thank you for your kind attention.